We look at the spherical coordinate system. We consider a right-handed Cartesian axis to begin with. So the x, y, and z are the right-handed Cartesian axis on which we impose a sphere. The sphere is shown in dotted lines. The spherical coordinates of the point P, this is the point P, its spherical coordinates are r, theta, and phi, where r is the length measured from the origin to the point P, as shown here. Theta is the angle from the z-axis. The direction of increasing theta is shown. And phi is measured from the increasing x-axis, positive x-axis. This is the direction of increasing theta. So when the system under investigation has spherical symmetry, then the spherical coordinate system is used. Systems governing equations assume the simplest form when its symmetries are used to model them. The system under question could also be modeled using other coordinate systems, and if that was done, then the equations will not be in the simple form. If symmetry is used in the modeling, then the system's equations take the simplest form. So if the system's governing equations assume the simplest form when its symmetries are used to model them. Here we have used a right-handed coordinate system, and the word Cartesian actually comes from René Descartes, a French mathematician. Now we look at the coordinate surfaces. So r equal to constant, when r is kept a constant, it defines a sphere of radius equal to r. When theta is kept a constant, when theta is constant, then the vector spins a cone, a half cone, not a double cone, but a half cone. When phi is constant, we have a half plane. When phi is constant, you have a half plane shown here. When theta is constant, you have a half cone, not a double cone. And when r is constant, you have a sphere. Let's look at the unit vectors of the Cartesian, of the spherical coordinate systems. The AR, A theta, and A phi are the unit vectors of spherical coordinate system. So AR is a unit vector along the r direction, as shown here. And A theta is the unit vector along the theta direction. This is the increasing direction of theta. So A theta is that way, as shown. And A phi is, this is the A phi, and it is in the direction of increasing phi. So these are the unit vectors and their directions. So the differential curvilinear cube formed by the spherical coordinates is shown in this picture. The sides of the cube are also shown. So along this side, with the differential dr shown, is the dr element along the direction of r. So r, theta, phi are again shown here. So dr is in that direction. D theta, r d theta is the side, is this side, and r sin theta d phi is the bottom side of the differential curvilinear cube. So using these dimensions of the differential cube, it is possible to compute the surface areas of the differential element. So r dr d theta, for example, is the area of the face formed by dr and r d theta element. So this face. Equivalently, the other side, which is not visible in this picture. So its area, this face's area, is product of the two sides, r d theta and dr, which is r dr d theta. Likewise, the surface areas of the other faces of this differential curvilinear cube may be computed by multiplying the corresponding sides. So if I multiply r d theta and r sin theta d phi, I have r squared sin theta d theta d phi, which is the area of the front face, this face. Equivalently, the area of the back face, which is not visible in this picture. So the volume element of this differential curvilinear cube is obtained by multiplying the differential sides, that is multiplying the three quantities shown here, dr, r d theta, and r sin theta d phi. When multiplied, give us the volume element, which is this one, r squared sine theta dr d theta d phi. Now the transformation from Cartesian to spherical coordinate systems. So if the spherical coordinates of a point are given, that is r, theta and phi are given, then the x, y and z coordinates are the Cartesian coordinates, which may be computed by using these equations. These are spherical to Cartesian transformation equations. Likewise, it is easy to show that the inverse transformation, that is, when the Cartesian coordinates are given, then the spherical coordinates may be computed by using these three equations, which are easy to calculate, which are easily computable by using the first three equations. Now, the unit vectors ax, ay, and az have their components along the ar, a theta, and a phi directions. So ar, a theta, and a phi are the unit vectors in the spherical coordinate system. So the ax, ay, az have their components along ar, a theta, and a phi. The az component, for example, may be computed along ar, a theta, and a phi by taking the dot product of az with the unit vectors ar, a theta, and a phi, and it works out to be cos theta minus sin theta and 0, which are shown here, cos theta minus sin theta and 0. So these are the components of the az unit vector in the Cartesian system along the unit vectors of the spherical coordinate system. In similar manner, the ay and az's components may also be computed, and they are listed here in this table.